A very warm welcome to all of you. Myself Rajan Choudhary, Professor in the Department of Civil Engineering, Indian Institute of Technology, Guwahati, instructor for the NPTEL MOOC course Pavement, Construction and Technology funded by Ministry of Education, Government of India. Our today's lecture, which will be on mixed design of bituminous bound courses, will be a part of our module 4. And at the very beginning, I acknowledge the use of text, information, graphs and images sourced from various textbooks, codal standards, journal articles, reports, newsletters and public domain searches. Beginning with the design of bituminous mixes, as we discussed in the previous lectures where we discussed about the unbound courses also, there is a requirement of achieving a combination of materials, and that combination is target to achieve some desired characteristics in terms of the strength or in terms of any specific performance, which can be say the maximum load it can take. There we discussed about the unconfined compressive strength, we discussed about the CBR, the requirements were in terms of the CBR, it can be in terms of the density also. So, when it comes to bituminous bound mixes, as the term is there, you have aggregate, you have bitumen with us. So, you have to work out the combination to get your bituminous mix. This is what a design of bituminous mix. So, you need to first work out what combination of aggregates are suitable for a particular layer. And layer means you have every layer have you want every layer to perform well when the traffic load comes under different environmental conditions. So, this what combination of aggregates can be there in terms of different sizes, and once that particular combination is decided, what amount of water is to be added to those aggregates, and finally to get a mix. At all stages we need to ensure, we discussed in previous lectures about how we can ensure the quality of the aggregates, we discussed how we can ensure the quality of binder. Here we will discuss how we can get an idea about the properties of the bituminous mix which we get. So, these are the different steps which are involved in the bituminous mix design, and ultimately my design, what I am targeting out of this particular design, with this blend of aggregates and binder which I'll decide in this under this mix design, I want to have a good stable mix. Good stable mix means when traffic comes over it, it should not show these deformations or it should not show these kind of cracks. These cracks resembles very much resembles to the skin of an alligator. So, you can see an alligator is there and these cracks are there. So, these cracks you can see there is some flushing is there, the binder has come up on the surface, you can again see some amount of depression and a flushing is there, again the cracks are there, some amount of depression is there. This is construction of bituminous mix is going on. These are in laboratory compacted specimens, because I need to work out the different properties of the mixes at laboratory scale before suggesting that particular combination for construction in the field. So, my mixed design, I'll prepare a mixed design and ensure it meets all the desired requirements, then that will be followed in the field. So, one requirement is the stability. Second, it says, because I am going to add binder, I very well know if that binder is there, that is the one which is holding those aggregates together. Now, this how much quantity of binder, more binder will require will add more to my cost, and whether it is by increasing the binder to those aggregates volume, whether I am adding some gain in the strength is there, or in addition to the gain in the cost, because cost definitely will increase when you are going to increase because binder is the costliest component in your bituminous mixes. Now, so I need to work out a bituminous binder volume or quantity which is good enough to provide a good cohesion, because the material has to have a good cohesion. It should, because if good cohesion is there, then only it can take a good load. It should be flexible enough. If it is very stiff with a small amount of deflections, it will crack down, because we have granular courses all. So, there will be some amount of deflection which will be there. If the material is very stiff, it can crack down. In addition to that particular one, as we discussed during the binder characterization, aging of binder is also important. If the film, if the quantity of binder is quite low, then the formation of film will be again very thin over the aggregates, and that thin film will be more prone to aging or oxidation compared to a thicker film. And in addition to that particular one, this is the coating should be good enough so that the aggregates surface does not get exposed in presence of water. So, I need because aggregates in general have a more affinity towards water compared to bitumen. So, I require a binder content which should be optimum in the sense it should give me the cohesion, stability, flexibility, it should give me moisture damage resistance, it should give me the aging resistance also. And if you add a quite higher amount of binder, it may lead to a reduction in the stability also, because your structure units are your aggregates. So, there is a specific range or there will be a specific quantity of binder which will be good for a mix. So, that needs to be worked out. So, what you need to see? You need to see the asphalt content which is appropriate for a mix. You need to see that it gets a good strength out of it. Air void content, when you prepare these bituminous mixes in lab and field, there will be some air entrapped in this particular one. They will not be completely voidless mixes, there will be voids, and these voids, but a general conception is that if a mix is dense, the more the dense it is, the more strong it will be. Yes, with the increase in the density, the strength load carrying capacity can increase, but here there are certain challenges also which needs to be understood. Challenges are because when you are having this particular mix to a higher density, if during the aggregate blending itself, if you are making a very dense aggregate packing, then there will be no space for binder to enter into it. Your durability will be a concern, because then the aggregates will not get a good coating over the binder of binder over them. So, you need in your aggregate blend a good amount of air void content also. In addition to this particular one, once the mix is compacted during initial years, there is some amount of secondary compaction which happens by the traffic. That usually happens in the initial periods of 2 to 3 years of life. So, some densification because of the reorientation of the particles by the movement of the traffic, some secondary compaction takes place, and little bit amount of binder expansion also can take place, especially in hot summers. So, that is why we require some specific range of air void content also. So, this is also a part of your mix design, and whatever mix you are preparing should be workable enough, because ultimately it has to be laid in the fields by your conventional pavers and compacted through your rollers also. So, that mix should be workable for laying and compaction in the field, and if you are using that mix as a wearing course, then it should give you a good skid resistance also. So, these are certain requirements of which you look from a bituminous mix. Some of these we will try to address at the design stage itself. So, first, aggregate gradation, as in the case of granular courses also, here aggregate gradation is very important. As I mentioned, that the general conception is that if I have the gradation yielding the densest aggregate particle, it will be the most desirable one. Why? Why this conception is there? Because such gradations typically enhance mix stability by maximizing interparticle contact. When they come close together, then their interparticle contact is more, their load transfer is better, and minimizing voids within the mineral aggregates. So, this is a normal conception. While maximum density gradations improve stability specifically, the load, but they may not allow adequate space for the bitumen to ensure long term durability. So, then those mixes, because there already the void in that aggregate gradation is quite low. So, there is no space for the binder to form a good film over the aggregates. Insufficient air voids can lead to issues such as bleeding or rutting, because when the secondary compaction takes place, reorientation of aggregates takes place, expansion of binder takes place. If there is no air void available, then that may lead to specifically rutting or flushing or bleeding in that case. Flushing is when the binder comes over the surface, that is the or all air voids are filled with bitumen, of a mix, and the binder is you can see dark patches of binder along the, specifically along the wheel paths. And rutting is when deformation along the on the pavement surface is there, which mainly happens along the wheel paths, where the common wheel paths which are there. So, the wheel always will have dense gradations, but will try to ensure that this gradation should have adequate amount of air voids to accommodate the required quantity of binder also. So, these dense gradations tend to be, and even if the gradations are more dense, then they are highly we can say they are highly sensitive to the variations in the binder content also. So, and this binder content can happen specifically when you are doing the productions there at hot mix plant. There may be a slight variation. This is and we give a allowable range. Whatever we do at laboratory scale, it is cannot be exactly simulated in the field. So, we need to allow some variation in the field. So, with that, if the densest gradations are there, they are more vulnerable or sensitive to the change in the binder content. So, therefore, to have a balance between stability, durability and workability, we normally try to deviate from the densest packing which we can have, so that we get the required amount of air void content in our gradation to accommodate your binder and to look after the aspects related to secondary compaction. Now, certain parameters needs to be worked out for this bituminous mix design. One is required to know the specific gravity of the aggregates and binder. So, for aggregates, the specific gravity which is required is bulk specific gravity. We discussed earlier also what is bulk specific gravity. When here this is an exaggerated view, when all the surface voids of an aggregates which are water permeable gets filled with water, there is no surface water. So, it is a saturated surface dry condition. This is so. For this particular case, the specific gravity which is determined oven dry weight, volume of aggregates plus the surface voids filled with water, that gives you the bulk specific gravity. The other one, if there is no water absorption considered, then what we have is the apparent specific gravity. So, this is already given in our IS 2386 part 4 which is there, as well as for the determination. Similarly, you need to work out the specific gravity for your bitumen also. So, this is one is considering the surface voids which gets filled with water as a part of aggregate, that is known as your bulk specific gravity, and this is one which is the used during the mix design exercises, and this is just for comparison to show what is the difference between apparent specific gravity and GSB. Now, if you have, I'll blend one, I may have stockpiles of A, B, C and D. 4 aggregates may be there. So, and I require to blend these aggregates to get my desired gradation. So, there I may be using in my 100% of aggregate blend, I may be using 20% from A, 30% from B, then again 30% from C and 20% from D. So, this is the individual percentages. So, my small a will be 0.2, 0.3, this we discussed, C point in fractions. Now, this combination I have to work out. Now, if I'll work out the specific gravity of this aggregate stockpile, I'll work out the specific gravity for this one and specific gravity for this one. There are measures for working out this specific gravity. Test procedures, as I mentioned, IS 2386 part 4 gives the test procedures for determining the specific gravity of aggregates of different sizes. So, for A you will have a range of particles. So, you will determine the specific gravity of that particular blend of A, which can be mentioned as GSB1, or I can write it as G1. I am referring here bulk specific gravity. So, always I will prefer to write as GSB. You can write as G1 because we do not use apparent specific gravities in the computations, and then here it is G2, G3, G4. Now, if I blend them in this 20, 30, 30 and 20%, what will be the specific gravity of this blend? So, this is how we get it. So, if you have say 3 aggregates used P1, P2 or more than that, So then you will write this will be your 100, because all that needs to be combined to become your 100%. And this is your individual shear. P1 is the percentage of the first particle or the first stockpile in the total one. So here if it is A, it is 20%. So P1 is the within that aggregate blend, what is its share. P2 is the second share. So P1 individual percentages of each aggregate fractions by total weight of the aggregate, and the G1, G2 are individual bulk specific gravity. So once this is there, so you work out the individual bulk specific gravities of each stockpiles, and then you determine the combined bulk specific gravity of that blend. There is another thing. This is when I am using a water and I am seeing the water absorption, so I got my bulk specific gravity. But when I will be preparing a bituminous mix, there will be no water, there will be an aggregate and binder. So can the bitumen get absorbed in the similar quantity as water is getting absorbed? It may or it may not be, but for in general I will feel, because binder may not go up to the same depth or may not get filled to the same level to which water will go. So therefore some of the surface voids, if a bitumen is added with the aggregates, may remain unfilled. So you can see the same aggregate parts, certain white portions are there. This shows the voids, surface voids. This is an exaggerated view to explain, to give you an idea that certain amount of binder may get absorbed in your surface of the bitumen, surface voids of your aggregate, but that absorption will not be to the same level as water is getting absorbed. So GSB, there is another specific gravity which needs to come into picture when we are working out with bituminous mixes, because the aggregates will not be submerged in water, they will be coated with the binder. So this comes out your effective specific gravity. This is neither your apparent specific gravity, this is neither your bulk specific gravity. And what it says, it is the oven dry weight divided by the volume of the your solids plus the volume of the voids which are not filled with the bitumen. So it says this when we look for this is your weight of oven dry weight of your aggregates and this is volume of solids plus volume of voids which are impermeable to bitumen. So I'll use this one and I'll use this one. So there is why it is important to determine this particular one, then these surface voids will be filled with bitumen. So some amount of bitumen goes into the surface voids that you need to work out, because this bitumen will not be available for coating the aggregates. If more amount of binder goes in certain type of aggregates, then even if I put the same quantity of binder for a particular weight or volume, then the more amount of binder gets absorbed in a particular type of aggregate and less binder is available for coating. So I need to know what can be the amount of binder which gets absorbed. So for this particular one, there is an expression which is given for which you need to determine the maximum specific gravity of the mix. You can see there are two parameters which are mentioned. One is the specific gravity of the loose mix. For this you cannot do directly a test on aggregates to get the GSE value. You have to prepare a loose mix where aggregates are mixed with binder and then you determine your effective specific gravity. So for this particular one, what you require here is your maximum specific gravity of the mix. This I will discuss in upcoming slides. Then we will again discuss this particular GSE part. So now important here we can understand, it says it is the ratio of oven dry mass per unit volume of aggregates including impermeable volume plus water permeable not filled with bitumen. So this is the impermeable one plus the one which are permeable to water but not permeable to bitumen. So, it is including impermeable volume, this is impermeable, plus water permeable not filled with bitumen. These voids were water permeable, but were not filled with the bitumen. So, this is what the specific gravity, effective specific gravity. For binder, determination of binder specific gravity, it is as per IS 1202. So, here these pycnometers, small pycnometer bottles are used. It is a conventional method we do for fine aggregates also, specific gravity measurements by using pycnometers. These are small pycnometer bottles. Here you have an empty pycnometer bottle, the second one filled with water, the third one first filled, half filled with a bitumen, approximately half filled, and thereafter remaining part is filled with the water. And I need to work out the specific gravity of bitumen. So, what is required? I need to know the first the weight of the bitumen, which is C minus A, because here half filled and this is empty bottle. Then I need to work out the volume, which is equals to this volume of this bitumen. So, what I am doing here is B minus A is giving me the water of this water which is there in this particular pycnometer. This is your B minus A. This through this water I will subtract out from D, I will subtract out C, so that will give me this water. So, from this total water, if I subtract out this water, I will get the volume which is corresponding to my bitumen sample, and this what comes on the denominator. So, you get the specific gravity of binder. So, this is now you have a specific gravity of aggregates with you, you have the specific gravity of binder with you, you have a specific gravity GSB, you have the specific gravity of aggregates, of the blend also, and for individual aggregates also, and you have the specific gravity of bitumen, which is only thing which we will further discuss is the GSE, effective specific gravity of aggregate. Once this is there, you need to prepare a aggregate and a binder blend. Now, for this one, the aggregate proportioning already done to achieve a particular gradation. Now, I need to prepare a mix. So, for laboratory testings, specimens are prepared and which are cylindrical specimens, and the very common specimens which are prepared are having 4 inch of dia and around 2.5 inch of height. Now, for this particular one, cylindrical specimens which are in this particular manner, where this height will be, this have to be approximate, because I need to have this one. So, this is 2.5 inches of height and 4 inches of dia. Now, for this particular cylindrical specimens, approximately 1200 gram of aggregates are taken for these specimens to be prepared, and these we need to do some determinations, especially volumetric measurements, to come to this particular design of bituminous mixes. Now, for this one, we will prepare these cylindrical specimens, will take around 1200 gram of aggregates, and then we need to start with a trial binder content. For different mixes, already the codal specifications, whether it is your IRC 111, which is on dense gated bituminous mixes, your MORTS, they gives that these mixes should have a binder content which can be more than this one, they give a range also. So, for an example, here for preparing a blend, because we need to understand what volumetric determinations are there and how it is done. So, let us go for a binder content of 6% by weight of your mix. Now, for this particular one, what it means that if I have taken an aggregate of 1200 gram and I want to have a binder which is 6%, then what I will do, I need to work out the total mix weight. So, the total mix weight in this particular case will be 1200 divided by 1 minus this is 1 minus the 6% divided by 100. So, you will be have your total mix weight will be 1200 1 minus PB by 100. PB is your percentage of binder. So, here I took 6% of binder. So, this particular one became 1.06. So, I got the mix weight as 1266. Now, aggregate weight was my 1200 and my total mix weight is 1276 point. So, what is the my weight of bitumen which I have to incorporate is 76.6. 6 grams. So, if 70.6 grams of binder is there in 1276.6 gram of mix, then it makes 6% of bitumen. So, and I always prefer to have these binder contents with respect to my mix weight. You can have with respect to aggregate also, but for mix design computations you will find it is easy to work out with respect to the total weight of the mix. So, here now if I need to prepare a mix with 6% bitumen content, I will take 1200 gram of aggregates, I will add 76.6 gram of bitumen, whichever grade of bitumen VG 10, 20, 30 which you have already selected, or any modified bitumen, and you will mix with it. There is a standard process, there are standard protocols for mixing it, at what temperature you should heat your bitumen, at what temperature you should heat your aggregates, and then it has to be mixed in a laboratory mixer. Then you need to transfer it to ovens where conditioning is done. The conditioning here, this is the drying of aggregates. Similarly, after this particular one, you do the conditioning of this loose mix, and then it is compacted. So, when it is compacted, you apply a compactive effort, then and that compactive effort should be the one which can give you a density which will be there after 2 to 3 years of service life. So, this is what now this you can see my loose, this combination of aggregate and binder, when compactive effort was given, this cylindrical specimens got prepared. Now, for this considering the usual specific gravities which we have for aggregate and for binder, we normally will get the dia because it will be prepared in cylindrical molds. I will show you later on cylindrical molds. So, the dia will be exactly same, only there may be a small variation in the height of the specimens. Once you have this particular one, this is a prepared compacted bituminous specimen, and the density should be the one which is after the secondary compaction. If this mix is laid and compacted first in the field by rollers and thereafter some secondary compaction, then the density after 2 to 3 years of life I will target to achieve the same density in the laboratory. Now, once I will try to show in a phase diagram this particular one, where I can, if this is a diagram which shows my different volume of different components, I may have the volume of the aggregates which is at the bottom. Then there will be some amount of asphalt, volume of asphalt which is free, and some amount of asphalt which has went inside the aggregates, which I will call it as an absorbed aggregate, absorbed bitumen or absorbed asphalt, and then definitely some amount of air voids are also there. So, this is a phase diagram where you show the volume of the different phases which are existing. So, what I am mentioning here, this is my Vs is my volume of aggregates, specifically this is the volume corresponding to the bulk specific gravity, because to a certain extent the binder goes inside it, and so I'll mention this is my volume corresponding to the bulk specific gravity or volume of my solids, including the surface voids. So, some amount in those surface voids, some amount of binder has gone. So, the volume of asphalt, some has gone inside the aggregate surface, some part is free. So, if this is my total binder, out of which this VBA is the one which got absorbed, and VBE is the binder which is effective, or I can write it as VBF, binder which is free, and VBA is the binder which is absorbed inside the aggregates. And what is there on the top? It is your air. Now, another important parameter which is here is voids in mineral aggregates, VMA. This is when the aggregates are packed, what is the space which is available in that compacted specimen for the free asphalt and the air. This forms your voids in the mineral aggregates, because there you have your free asphalt as well as your air. Now, this makes your total volume. This is bulk volume of your mix. Now, if I put in terms of weight, this will be my this volume of aggregates will correspond to the weight of the aggregates. This volume of bitumen including the absorbed bitumen will be my weight of bitumen, and this will be my total weight of the mix. So, these are the important. Now, under this particular mix design, I need to determine few parameters. One is the air void content in that particular compacted mix. How much air void? Because as I discussed in the beginning, for me it is important to control the air voids, because there is some amount of secondary compaction also going to happen, and some extent of the binder expansion also there. So, I want to keep a particular range of air void content. So, for that I need to know how much air void content is there. I need to work out the voids in the mineral aggregates, because this void is important. Here only my binder is available, free binder which is going to coat the aggregates is available, and the air voids is. So, for me this voids in mineral aggregates is important. Voids filled with the bitumen, because out of this total voids which includes asphalt, I need to know the share of the asphalt also, so that I can get an idea about the how much coating is possible. I want this share to be, at least a good share should be there in this VMA from this asphalt, the volume of the asphalt. And then I may require to know about how much binder is getting absorbed. So, percentage, I may look into the percentage of binder which is getting absorbed. I not prefer for aggregates which have a high water absorption, because it will increase the cost of my mix. And then one may ask, okay, considering how much binder has already absorbed, can you tell us the percentage of binder which is free or which is effective, which is available for coating the aggregates. So, similarly, so this shows these are the three components which have been shown. Now, here important, we already discussed voids in mineral aggregates. So, if I remove this from this particular one, if I remove this binder, whatever this binder and air part which is there will be my VMA. Will be my VMA, free asphalt plus air. This is my voids in mineral aggregates. Are the small air pockets between the coated. Now, if I look for what is this air, then this air are the small air pockets which is trapped between my bitumen coated aggregates. So, and the proportion of voids in mineral aggregates filled with the bitumen is termed as voids filled with the bitumen or voids filled with the asphalt. As I said, people, these are synonyms: asphalt binder, bitumen, bituminous binders. Now, these all needs to be worked out, and as I mentioned, when I will be looking into this weight, I will have weight of aggregates, weight of water, which will make total weight of mix. Weight of air is taken as being 0. Now, you have the compacted specimens. So, the density of that compacted specimens can be measured as while preparation. I was knowing that how much amount of I prepared the mix with using a 1277 6.6. So, when I prepared the mix, I used 1276.6 gram of mix. So, I know the mix weight. Now, here I need to determine the specific gravity of this particular one. There are ways of doing it. One conventional which can be done for solid things is you mention, because its dia is fixed, you measure its height, so you can get this volume of this specimen. But this is not the correct manner, because you will have many surface voids which are there, and they becomes a part of this particular mix if you are doing it from dimensions. Here I am just measuring the height. This gives you height, and this gives you diameter, and then if I work out the volume as pi by 4 d square into h, then this will give me volume of this one, but this volume will be more than what is there, because already those surface voids which are present also become a part of this specimen, which in actual are not a part of this specimen. So, you will get, if volume is more, you will get a specific gravity which will be less, because your weight remains same. Mass of aggregate and asphalt, here for our specimen it was 1276.6 gram. Now, the good way of doing it is water displacement technique, where you measure the weight in the air and you measure the weight in the water. The loss in weight is equals to the weight of the volume of water which gets displaced, which you might have done these experiments in your school days of where any volume of a substance in water. When you dip any particular object in water, its weight gets reduced, especially because of the buoyant force. So that particular application is here. Here we'll see what is the loss in weight is there. That should be equal to the volume of the weight of the volume of water displaced. So then I get the volume of that water, which is equivalent to the volume of the specimen, and this will give me the correct. So here this particular one, I'll determine the saturated surface dry, which exactly gives only those surface voids which are part of the specimen, and then I'll dip it in water. I'll get the bulk specific gravity of this specimen. So once this bulk specific gravity of the mix is there, so these specimens will be prepared, and through this water displacement technique you will get the volume of it. So I'll get a GMB, which will be my weight, which weight was already given to me, and this volume of my mix, bulk volume of my mix. In addition to this one, this is the compacted mix. I need to know a mix without any air void. So for this particular one, I want to measure the specific gravity of loose mix when there is no air void in it. So before compacting, I can do it. So for this one, I'll prepare some loose specimens with the same binder content, having 6% to 76.6 total mix weight, and there are techniques which are used for determining the specific gravity, and we call this a specific gravity as maximum specific, not as theoretical maximum specific gravity. We will refer it as maximum specific gravity. So the maximum specific gravity is determined especially of loose mixes, and here for the loose mixes there are different techniques which are used. Two most common are the rise specific gravity method, and the third is automatic vacuum sealing method. Here the loose mix, in the basic concept behind is, in this loose mix is submerged in this rise specific gravity meter, you submerged it in water and you apply a vacuum to trap out or to take out all the voids which can be there inside this particular loose mix also, and then you get the weight of this loose mix in air and the weight of this loose mix in water without any air voids. So that will give you the volume of this particular loose mix. Here in a vacuum sealing method, the loose mix is taken out, and through the vacuum application all the air voids are taken out, expelled out, and then this loose mix is submerged in water, and you get the weight of the loose mix in water, which gives you the volume of the loose mix. So you work out the specific gravity of this particular one, GMM, in this manner. Now once this GMM is known to you from laboratory methods, these are two laboratory methods where you actually prepare a loose mix and you determine the maximum specific gravity. So then you can work out the specific gravity, which takes care of only the voids which are not filled with the bitumen, as we discussed earlier. So if GMM is known to us from this particular measurement, then this GSE can be determined. Here the expression of GMM is given in terms of GSE, but otherwise I am going to determine the GMM from these laboratory experiments. Once I am able to get it at one binder content, at other binder contents I can, without doing this exercise. So if I am having, I will show you, okay, if I am having say GSE determined, this GSE will be in terms of the total amount of materials. This is explained in the coming slide also. I will give you PMM minus GMM, PB upon GB. So once what this expression is here you have the maximum specific gravity which you determined through the laboratory method. This is the specific gravity of binder, this is the percentage of binder, this is the total percentage of mix, which is 100. So 100 minus your percentage of binder, in our case was 6, and then this is again 100 divided at the denominator, 100 divided by GMM, which you have determined by any of these laboratory methods, minus PB is your 6 and divided by specific gravity of bitumen. So with this particular one, the your numerator is this, your denominator is this, you work out your GSE. Now this is an aggregate characteristics. So the how much amount of binder an aggregate can absorb, this should remain more or less constant, should not vary significantly, but yes, with the amount of more binder available, slightly this particular one GSC value will increase, because more binder gets absorbed, goes up to a higher depth. But I can, for my ease, because otherwise for all different binder contents I need to work out this GMM. So it is a time consuming. What normally people do is they determine the GMM at one binder content and then they determine GSE. Once this GSE is known to you, from this expression you can reversely work it out and you can figure out the GMM at other binder contents. So this was my 6. Now for at other binder contents also I can work out if the GSE is known to me. So it is done in this particular manner. Now I have my maximum specific gravity GMM of the mix, I have the bulk specific gravity of the mix. So how much air void content will be there in this particular mix, that I will work out as. This will give me my air void volume with respect to the volume of the mix. And so whatever these air voids are there, I am trying to work out the volume of these air voids with respect to my total volume. So this will be in percentage of it, which I will get. This is important. I need to see how much air voids I am having in my mix. Second is VMA. For this VMA, voids in mineral aggregates, as I mentioned, the volume of aggregates will be there. When VMA is there, it is that particular portion which will have your free bitumen as well as your air void also. So that I need to work out, and this VMA will be your 100 minus this is your bulk specific gravity of mix, and this is the bulk specific gravity of your aggregates. Then when we work out the voids filled with the bitumen, VFB will be your VMA minus your VA divided by VMA. This is how much share of these voids in mineral aggregates are filled with binder. So this VMA, what my VMA was having? My VMA was having this free asphalt with me. This is my free asphalt and was having my air voids. Now what I want to ensure out of it, how much percentage of this free asphalt is there in this total volume. So this is what, so for this particular one, VBF plus VA is your VMA, and what is your VA will make your volume of free bitumen. So this is what is your volume of free bitumen determined in terms of percentages. Then as I mentioned, in certain cases we need to work out the amount of binder which is absorbed in the aggregates. For this particular one, you need to know the effective specific gravity and the bulk specific gravity already. Now since GMM is determined, you know the bulk specific, this effective specific gravity. So from this particular expression, you get the percentage of bitumen absorbed in your mix. Now once here GSE is the effective specific gravity and GSB is the bulk specific gravity. So I just want to see in the surface how much amount of binder has gone, and this is with respect to the weight of total aggregates. Other parameters which I was working out was with respect to the weight of my mix. Here this is expressed as a percentage by weight of aggregates rather than a percentage by total weight of mix. And then finally, once this PBA is there with us, you can work out how much is the effective binder, because effective how much is free with respect to the total weight of my mix. So for this particular one, PB is the actual binder content which you have inserted. For that example, we took 6%. PS will be in that particular case, remaining will be your aggregates, percentage of aggregate is PS, and then whatever PBA you are going to work out will be mentioned here. That gives you the percentage of bitumen which is effective or which is free and available for coating the aggregates with respect to the weight of the mix. So here you see this is Pb is the percentage of effective binder in the mix, total weight binder less the binder absorbed, and this is with respect to the weight of the mix. So, these are some important parameters. Once you prepare a compacted specimens, you determine the bulk specific gravity of the compacted specimen, and simultaneously from the loose mix you get the GMM. So, and for the aggregates you are having the GSP with you. Now, once GMM, the maximum specific gravity of the mix is there, you work out the effective specific gravity of the aggregates. Then from those particular one we are working out the voids which are there in the mineral aggregates, voids filled with the bitumen, percentage of bitumen absorbed, and effective bitumen content. So, remaining part will continue in the next lecture. Thank you.